Hello and welcome to this lecture on the introduction to spectrophotometry. Here we are going to introduce waves to you. We're going to introduce some properties of waves, what waves are, and how we can describe them and use them in our instrumental analytical chemistry. So with regards to waves, there are various ways that we can use them. They typically make up the varying forms of spectroscopy. They're utilized in all of them, whether it be through absorbance measurements, emission measurements. Most of them involve waves of some kind. Now, they're not always light waves. Sometimes they are UV-vis waves. Sometimes they are radio waves. Sometimes they are microwaves. So spectrometric methods are a large group of analytical methods that are based on atomic and molecular spectroscopy. And spectroscopy then deals with the interactions of various types of radiation, mainly electromagnetic radiation with matter. And then spectrometry and spectrometric methods refer to the measurement of the intensity of radiation with a photoelectric transducer or other types of electronic device. So electromagnetic radiation is what we will mostly be using. Electromagnetic radiation covers a broad range of different wavelengths, from visible wavelengths, including things like ultraviolet, infrared, radio waves, microwaves, and so on. So this is energy with a wave-like character, and it can be characterized using several different terms, one of which is wavelength, often given the Greek letter lambda. And this is a length, so you'll often see it expressed in terms of angstroms or nanometers or meters or centimeters, because it is a length. It is just the length of the wave, and we'll see exactly how that corresponds to each wave in a moment. Then we have frequency, which is given the Greek letter nu. We have velocity, often given the letter v, and amplitude, which is the height of the wave vector at any particular moment along that wave. So here is a typical wave. This is a sine wave, and it is the red line here. So you can see that it oscillates around this central black line. It has both positive amplitudes and negative amplitudes. The negative amplitudes, the peak here is called a trough, and the peak at the top is simply called a peak. So this is the positive part, and this is the negative part. Now, they're not really positive and negative in the sense that we have negative numbers or positive numbers. Really, what it means is it's a different expression along this projection axis. So this x-axis here is actually the projection axis of the wave. So it is precessing in a direction. The waves move in a certain direction. So the distance between any 2 points on a wave, whether it be 2 peaks or 2 troughs or 2 intercepts, 2 nodes here on the axis, that is going to be the wavelength. So it is from one point on a wave all the way until that point is repeated again. So you can see here, this would be a complete wave, okay? The amplitude then is sort of like if we choose a point along this axis and then we go from that axis to the point on the wave, that would be the amplitude at that particular point. So the amplitude is the length of the electric vector at a maximum in the wave. Then the period is going to be P in time in seconds required for the passage of successive maxima or minima through a fixed point in space. Then the frequency is the number of oscillations of the field that occur per second and is equal to 1 over P and is given the units of reciprocal seconds, so seconds to the -1, or hertz. So basically it's the number of waves per second. So like how many of these complete oscillations do we have per second? That is the frequency. Wavelength then is given, as I said, the Greek letter lambda, and this is the linear distance between any 2 equivalent points on successive waves. So these are either successive maxima or minima, and it can have the units of angstrom, nanometer, or so on. It could be centimeters, meters, whatever. This A is supposed to be the angstrom. And then wave speed, so the speed of the wave is given as the velocity v is equal to f times lambda. So that would be the frequency times the wavelength. And so we would have, for example, meters per second there, or angstroms per second, or whatever. So another property of electromagnetic radiation is that it can propagate through a vacuum. It does not need any supporting medium. Sound waves, they require some sort of supporting medium, whether that be the air or it be water or whatever. It needs something to pass through. Whereas electromagnetic radiation, it can pass through a vacuum, much like in space. So that is why we're able to see this astronaut and also the Earth here. So electromagnetic radiation requires no supporting medium for its transmission and can pass through a vacuum. Electromagnetic radiation is a stream of discrete particles or wave packets of energy called photons. And photon energy is proportional to the frequency of the radiation. So a little on the mathematical description of waves. So waves can be expressed mathematically. They can be added together. They can be subtracted together. They can be offset from each other. Oftentimes, they're described in terms of angles. So sine waves with different amplitudes are shown here. They're different amplitudes because the height of the vector at successive maxima or minima is much larger than that of the red line. So the amplitude here is much less than the amplitude here because the vector here, which is just basically the straight line connecting the points between the axis of propagation and the maxima in the peak, they are going to be different. Then we have here the red line and the blue line. They're offset from each other by a total of 90 degrees. So that's about a quarter of a wave. So you can see here, or sorry, half a wave. So you can see here that the regular wave ends here, and then about 90 degrees later, we have the second wave here. So they're offset by about a quarter of a wave. Yeah, it was a quarter of a wave. So here is the full wave. So half a wave would be here, quarter of a wave is here. And so a quarter of a wave is 90 degrees, since an entire wave oscillation is given 2 pi or 360 degrees. So this is half pi between the offsets here. So the waves, as well as this, they don't propagate. So oftentimes we write this down on a page or piece of paper or a slide or whatever, and it's only in 2 dimensions. This is because of the limitations of paper or screen. But in fact, the wave actually processes through space in all directions. It is not limited to 2 dimensions. Now, there are things that we can do, and we will talk about that later, which can make it 2-dimensional. But if it is not controlled in that manner, we will have a precession of the wave in all directions about the axis of precession, which is this line about which the wave oscillates. So a wave can be described by an equation for a sine wave where we have y is equal to a sine omega t plus phi, where y is the magnitude of the electric field at time t, a is the amplitude of this, so like the height of the vector at any particular point. So here is the height. And then phi is the phase angle. So that's going to be the angle that the wave makes with regards to the with the vertical. And then omega is equal to the angular velocity of that. So this is then going to be, omega is going to be equal to 2 pi v, which is going to be equal to 2 pi v over lambda, where v is the velocity and of the wave. So that's like meters per second or whatever. Lambda is then the wavelength of the wave. So that can also be in meters. It can be in centimeters. The important thing whenever doing calculations of this nature is to make sure that you are using the same units for all of your lengths, and to make sure that your velocities are in the same units. It can be very confusing if you have a wavelength in angstroms and your velocity is in meters per second. You need to convert, most likely you'll convert your wavelength into meters. So the angular velocity is then related to the frequency of the radiation, like so. So you can see here y is equal to a sine 2 pi vt plus omega. So really all that's happened is that, or sorry, phi, all that has happened is that omega has been substituted into this equation, and we've got it in terms of the frequency of the radiation. And so here we have sort of what this looks like in a diagrammatic sense. So here is this sine wave that we were talking about before. Then we can relate this to the 3-dimensional picture. So this point in the middle is really this line that goes through. So if we look at it head on, so we're sort of rotating the picture here so that the wave is pointing directly at us coming out of the screen. And so the central point here is where the wave is coming out. And then we can express this in terms of the 360 degrees of the wave. So this is going to be the 0 point at the horizontal. Then this is going to be 90 degrees, 180 degrees, 270 degrees, and then back to the origin again of 0. And so you can see where these different points correspond to, because we can take like the waves, although they're processing towards us, it is not always true that it has always got the same amplitude when it reaches us. Like, for example, at some points, it will reach us with the maximum amplitude, but at other points, it will not. Radiation can transmit through any medium, but how it transmits will change. So what does this mean? Well, if we look at this example of radiation, electromagnetic radiation transmitting through different media, we have the transmission in air where the wavelength is equal to 500 nanometers and the frequency is equal to 6.0 times 10 to the 14 hertz. So this frequency is going to be unchanging, like the number of waves per second is not going to change. But what can change is this value of lambda, which is equal to 500. So it's the wavelength. The wavelength can be compressed or it can be expanded. So this is dependent on how the wave interacts with the medium that it is passing through. So here we have it passing through air and it has a wavelength of 500 nanometers. Then it passes through glass, but an interesting property of electromagnetic radiation is that it can expand again after it gets compressed in the glass and comes out in the air again. Its wavelength becomes 500 nanometers again. So the wavelength of this particular electromagnetic radiation in air is going to be 500 nanometers, no matter what has happened to it previously. So it started at 500 nanometers in air, and then whenever it reached air again, it again was 500 nanometers. But as it passed through the glass, it was compressed, and this was because of the interactions with the glass, compressing the wavelength and sort of affecting it and making it have a shorter wavelength. So the frequency here remains the same and the velocity and the wavelength change. So electromagnetic waves, so the velocity of the propagation is given here where VI is equal to the frequency times lambda. And so in a vacuum, the velocity of radiation is independent of wavelength and given by the symbol c. So c is the speed of light. And so that is equal to v times lambda, which is equal to 3.00 times 10 to the 8 meters per second, or can be given this in terms of centimeters per second. And so the wave number, nu, is the reciprocal of the wavelength in centimeters. So it's 1 over the wavelength. The electromagnetic spectrum. The electromagnetic spectrum encompasses an enormous range of wavelengths and frequencies, and spectroscopic methods are classified according to the wavelengths or frequencies that are important for analytical purposes. So here are some of the regions in the electromagnetic spectrum. So we have here the wave number, we have here the frequency in hertz, here the wave number in centimeters, reciprocal centimeters, and the wavelength m. You will find all of these in literature and in different applications, and they can all be interconverted. They're just units of convenience for the most part for different purposes. So in some instances, you may see wave numbers. Often wave numbers are common to be seen in things like infrared spectroscopy. Often you'll see wavelengths in ultraviolet or UV vis type measurements. And sometimes you'll see frequencies whenever you're talking about things like microwaves and radio waves. So here we can see that the high wave numbers or small wavelengths and high frequencies are things like gamma rays and X-rays. Then these are sort of higher energy regions of the electromagnetic spectrum. And then we move over here towards in the middle where we have relatively high energy, but not as harmful because these can be, if we have prolonged exposure to these can be quite dangerous to humans. Visible and ultraviolet can even be dangerous to us if we get too much exposure. Infrared, generally not that dangerous for humans. Microwaves and radio waves, again, not super dangerous. Radio waves are all around us, from our car radios, from our internet. Generally accepted that radio waves are not particularly dangerous to us. Regions are based on the methods used to generate and detect the various kinds of radiation, and the portion of the spectrum visible to the human eye is tiny when compared to the other spectral regions. So if you look here, this is a massive range of about 14 orders of magnitude, and we have here the visible in the center is only really, it's actually less than 1 order of magnitude. So there's less than 1,000 wavelengths that the human eye can see, like a range of like about, I think it's about 300 to 700, with some on the ends also visible. So the visible range is very, very small. But there are so many other kinds of radiation that are out there, that are surrounding us, that we cannot see. So here are some different forms of spectroscopy, their usual wavelength range, their usual wave number range, and the type of quantum transition that corresponds to that type of spectroscopy. So gamma ray emission, X-ray absorption, emission, fluorescence, and diffraction. So gamma ray emission is not really used that much, but the rest are, well, I mean, it is used, but what you're most likely to encounter are things like X-ray, UV vis especially, and infrared. To an extent, you might see NMR and ESR, depending on the applications. But generally things like UV vis, which is a combination of these two, and infrared, especially NIR, if you're involved with any kind of quality assurance type things, like near infrared is very useful for that, as we'll see when we get to our section on molecular spectroscopy. So for example, if we take the vacuum ultraviolet absorption and ultraviolet UV vis absorption, emission, and fluorescence, we see here the regions. This is typically looking at bonding electrons. So what's happening here is that these wavelengths in this usual wavelength range, they correspond pretty well to many of the transitions which occur within molecules and atoms to sort of excite one electron to from one energy level to another energy level. And if we're just measuring that particular part, then we're measuring absorption. But if we excite the electron and then measure the light that is emitted from a particular sample, then we're looking at emission. And fluorescence is a subset of that as well. So infrared then is looking at the rotation and vibration of molecules. So that's whenever bonds are stretching or they are rotating. And infrared absorption really only works for molecules. It will not work for atoms because there are no bonds involved. So because this wavelength range corresponds to the sort of transitions which occur, lower energy transitions than the electron excitations, but these will sort of like correspond to particular vibrations and bendings and things like that. Here we can see looking at what we just encountered, but in a little bit different way. So now we're looking at sort of the energy as well as the wave number, wavelength, and frequency. And so you can see that the energy involved with the gamma radiation is very, very high. Like you're talking huge orders of magnitude of energy. And then, so this is enough to really damage a lot of things, like it interacts directly with nuclei. And so this is where the danger comes, especially with regards to biological samples. They can be greatly degraded or destroyed entirely by exposure to this. Here we have like the radiation types in their boxes. So we've got gamma ray, X-ray, UV, visible, infrared, microwave, radio wave. And so that's kind of like how the energy goes. So the energy is lowest for radio waves, but they're also the longest. So they have a very long wavelengths. You could talk like hundreds of meters in terms of radio waves. And so that's not really, that's why they're generally considered to be pretty safe, because they don't have the energy that is required to really interact with any parts of our body. They just kind of pass through and go out and nothing really happens. And here again, we have the quantum transition types. So I talked a bit about earlier whenever we looked at that number line where we saw that many of the regions of the electromagnetic spectrum are kind of talked about in different terms, where we have things like Planck's, or sorry, like wavelength, wave number, and frequency. So how do we interrelate these? Well, what we typically use is something called Planck's equation, or Planck's relation, or the Planck-Einstein relationship. So this is the relationship between frequency of light and energy E. So E is equal to hv, or h nu, where nu is the frequency, and h is what's called Planck's constant, which is given in, typically the one we use is this joule second. So it's 6.6 times 10 to the minus 34, or 6.626 times 10 to the minus 34 joules per second. And then because of this relationship here, where the speed of light is equal to, so this is the velocity is equal to the frequency times lambda, we have the velocity of light, c, is equal to the frequency times lambda, is equal to 3 times 10 to the 10 centimeters per second, which gives us the velocity, or sorry, the frequency is equal to c over lambda. So then we can, since we have this new value here, or this new equation for nu, we can actually substitute this into our Planck's equation. And so it becomes EH, and then we put this term here. And so this now means that we can actually, instead of having to know the frequency, we can just know the wavelength. And because we know the wavelength, then we can get the energy. And so we can evaluate this out, and we can see that HC mu, where nu is equal to 1 over the wavelength, which is equal to the wave number. And so we find out that energy is directly proportional to the wave number. So superposition of waves. So if two plane polarized waves overlap in space, the resulting electromagnetic disturbance is the algebraic sum of the two waves. So what does this mean? Basically means we can add waves together, and but if their phases are different, then what ends up happening is they're destructive, they interfere destructively, and they destroy each other. So say we have these two waves here, we have wave 1 and wave 2, they're a little bit offset from each other, but because they have the same phases as they go through, so that means the positive parts broadly overlap with the negative, other positive parts. So you can see the peaks are broadly pointing in the same direction, and then the troughs are broadly pointing in the same direction. Because of this, whenever we combine these waves, or when these waves are passing at the same time, like they're passing through space in the same direction, they can be combined, and they create this black line, which is the sum of the two waves. Now, if on the other hand, we have two waves, this gray one and this blue one, but you can see that their phases are different and their amplitudes are also different. It means that they interfere destructively. So it basically means that the overall amplitude of the final wave will be less. But because 2 has a higher amplitude than 1, it means that 2 will dominate the expression of this wave in space. And so what will happen is that the amplitude will be pointing in the direction of wave number 2, the blue wave. But the amplitude, overall amplitude of it will be reduced because of the effect of the gray wave working in the opposite direction. So the superposition of a sinusoidal wave. So in A, we have A1, the amplitude of 1 is less than the amplitude of 2. And then they're offset by a certain phase angle, which is 20 degrees. And then velocity 1 is equal to velocity 2. In the case of B, we have the amplitude of 2 is greater than the amplitude of 1, but the phase angle is 200 degrees. So you can see that the peaks are offset dramatically. But at the same time, the velocities are equal to each other. And in each instance, the black curve results from the combination of the two other waves. So that's what I talked about. So here it is in a simpler sort of sense. So this is optical interference. So this is the combination of multiple waves. So we have constructive and we have destructive interference. So the optical interference here is the interaction of two or more light waves yielding an irradiance that is not equal to the sum of the irradiances. So here we have constructive interference. So they have identical frequency and the phase angles are equal to some value here. So if the phase angles are the same, then we're going to get perfect constructive interference. And in this case, they have the same phase angle, which means that the peaks and the troughs directly overlap with each other, which creates this system over here where we have a perfect doubling of the amplitude, because these have the same amplitude, they have the same phase, they have the same phase angle, And as a result, they perfectly overlap and they create this much higher amplitude wave. Now, this is destructive interference here on the right. And in this case, they have identical frequency and their phase angles are the same. But the problem is that their phase angles are different. But the problem is that because this one's troughs overlap with this one's peaks, we end up with perfect destructive interference because their amplitudes are equal. And so what ends up happening is we have destructive interference where the wave basically cancels out and we have no wave. And so this is one of the ways in which active noise canceling headphones work, is that they create a wave which has all of the components of the external noise. And so it basically cuts out any of the external noise by using destructive interference. Periodicity, or the beat of a particular wave. So the superposition of two sinusoidal waves of different frequencies but identical amplitudes are seen here. The resultant wave is no longer sinusoidal, but exhibits a periodicity. And so what happens is these two waves are kind of offset by half of the frequency. So you can see here this V2 and V1, so they're offset from each other. And you can see here the trough corresponds with the peak. Now, assuming they have different amplitudes, what will end up happening is that they will create this beat structure. So this is what happens within regards to music. So instead of it like being perfectly canceling out, perfectly destructive, or perfectly additive, i.e. constructive, then what will happen is that we'll have areas where there is a strengthening of the amplitude or an increase in the amplitude, and areas where there's a decrease of the amplitude so far that there might actually be no sound at all. And so we can see that wave one has a period is equal to 1 over V1, and then wave 2 period is equal to 1 over 1.25 V1. And so the result here is 1 over the difference. And so the difference is going to be the absolute difference in these two. So it's going to be V1 minus V2. So it would be 0.25 for delta V. So 1 over 0.25. So we'd have a result of 4. The importance of superposition then. So a complex waveform can be broken down into simple components by a mathematical operation called the Furrier Transform. And so the Furrier Transform was invented by Jean Furrier, or Jean Furrier. He's a Frenchman, and demonstrated that any periodic function, regardless of complexity, can be described by a sum of simple sine or cosine terms of the original signal. And so this turned out to be very, very powerful in spectroscopy because it meant that we could get the individual components out of a complex signal. And so the Furrier transform decomposes a function of time, a signal, into the frequencies that make it up. And the Furrier transform is called the frequency domain representation. And this is incredibly important in things like NMR, where it's able to take the radio wave and transpose it into a series of signals, which are going to be useful for us in terms of finding out which peaks represent which components, which hydrogen atoms, which carbon atoms, and so on. But Fourier transform is tedious and time-consuming when done by hand, and so efficient computer programs are necessary because computers are very good at doing calculations, especially if they're repetitive calculations, and so that can really sort of help with our calculations and our sort of like decomposition of a complex waveform. So different types of radiation. So we have coherent radiation, which is when two waves have an initial phase difference of 0 or constant for a long time, and they're considered to be coherent. So this means that they're passing sort of in the same fashion. And so conditions are for coherency of two sources of radiation are they must have identical frequencies, and the phase relationships between the two remains constant with time. So there can be no increase or decrease with the phase relationships, because otherwise this would eventually lead to some form of destructive interference. But we can also have incoherent radiation. So we can test to see if something is incoherent. If we illuminate the slits with a tungsten lamp and the result is the disappearance of the dark and light patterns or more or less uniform illumination of the screen, then we will have, we can see incoherency from a tungsten lamp. So we have these two slits and we create the two slits around the tungsten lamp, we end up getting the disappearance of the dark and light patterns, or more or less uniform illumination on the screen. And this behavior is the consequence of the incoherent character of a tungsten lamp. So things that are incoherent sources are light that is emitted by individual atoms or molecules. We have the resulting beam is the summation of countless individual events because they're not all absorbing light and releasing light at the same time. And so the phase differences are inevitable and they're very variable. We have both constructive and destructive interference, which is occurring randomly. And the average of the emissions is observed as an illumination. But we can have coherent sources of things like of sources of electromagnetic radiation. These are typically like optical lasers, RF oscillators, and microwave sources. So what's happening here is usually the lasing medium in a laser is being charged with some energy. And then once it has reached sufficient amount of energy, it starts to release light in packets. And these are always of the same size, and they're almost always with the same frequencies, and they are very, very coherent sources of light. Radio frequency oscillators are what used in NMR, and so they are also designed to give coherent sources of electromagnetic radiation. So radiation can transmit through a sample. So the rate of radiation propagates through a transparent substance is less than its velocity in a vacuum and depends on the kinds and concentrations. So here we have a medium. So that could be our air from earlier. It could be our glass, and we have an incident beam. And then this medium actually can change the direction through which the beam is propagating. But whenever the beam that has been transmitted through the medium exits again, this angle will return to the original. So we have an incident beam at a certain angle, say it's at 60 degrees to the medium here. Then we can see that, or 60 degrees to the incident angle. So the incident would be this vertical here. So say this is about 30 degrees. Then we have the medium, and then that changes the angle. So the incident angle changes, maybe becomes more narrow. So maybe that's about 20 degrees. But whenever we come back out again, it returns to the same angle to the incident as we had before, this 30 degrees. So the radiation must interact in some way with matter in its path, and frequency change is not observed. However, the interaction cannot involve a permanent energy transfer. Refractive index of a medium is one measure of its interaction with radiation and is defined as so, where n, which is the refractive index, is equal to c, which is the speed of light, over v, which is the velocity of radiation in the medium. So Ni is the refractive index at a specific frequency I. Vi is the velocity of radiation in the medium at that frequency, and c is its velocity in a vacuum. And since usually we're talking about electromagnetic radiation like light, then c would be the speed of light. Okay, so this is the end of part 1 on waves. So let's check our comprehension. So we're asked, what is the energy in joules of a photon with wavelength 340 nanometers? So remember earlier we had a particular point where we learned how energy could be calculated from a property of the wave. So pause for more time if you need it. We will go through the answer in a moment. Pause for more time if you need it, or we're going to go through the answer soon. Okay, let's check. So we're going to be using Planck's relation here, or the Planck-Einstein relationship. So the first thing we need to do is convert our nanometers into something which is consistent with our h value, this Planck's constant. So the first is to convert nanometers to meters. So the 3.40 nanometers becomes 340 nanometers, sorry, becomes 3.40 times 10 to the minus 7 meters. And then we use Planck's relation, which is E is equal to HV, H nu, or E is equal to HC over lambda. So we have a wavelength, so that's why we need lambda. So E is equal to HC over lambda, which is equal to 6.63 times 10 to the minus 34 joule seconds, times this C value, which is the speed of light, over this lambda value, which is 3.40 times 10 to the minus 7 meters. And then E is going to be equal to this. So it's 5.87 times 10 to the minus 19 joules, because we were asked for the energy in joules here in our question. And so this is how we would get the energy of a particular photon of light with a wavelength that is given to us. H is just a constant, so that would be in a table of constants that we would be given. C is the speed of light, which is usually given to us in a table of constants, although its value is fairly simple, so it's often quite easy to remember. So that is how we would calculate the energy in joules of a photon with wavelength 340 nanometers. Thank you for watching part 1. Stay tuned for part 2.